Hello everyone, I welcome you all for the second lecture on partial differential equations. In this lecture, I will discuss how to find out the general solution of first order partial differential equation, that is Lagrange partial differential equation, and numerical problem. In lecture 1, I discussed about the formation of partial differential equations. There are two methods: elimination of arbitrary constants and elimination of arbitrary function. Consider equation number 1 to 4. First one is equation of spheres with center on z-axis. Second one is of cone. And third one is equation of all surfaces which are symmetrical about z-axis. Equation number 4 is same as equation number 3, but we are rewriting it in a different way. And if you have gone through that lecture 1, then the partial differential equation corresponding to all these four surfaces is given by py minus qx equal to 0, and this is first order partial differential equation. It means if we have to find out the general solution of such type of partial differential equations, then there are two options. Either there are going to be two arbitrary constants, just like equation number 1 or 2, or there is going to be one arbitrary function in the general solution of the partial differential equation, as we have equation number 3 and 4. So in this lecture, we will discuss how to find out the general solution of partial differential equation given by 1. This is Lagrange partial differential equation. Here I am taking z as a function of x and y. And equation number 1, we have capital P into derivative of z with respect to x plus q, capital Q, derivative of z with respect to y. This is equal to capital R, where capital P, Q and R, they are functions of x, y and z. If you see this equation number 1, this is first order partial differential equation. So if we talk about its general solution, then the number of arbitrary functions will be 1. So next I am discussing theorem number 1. This theorem tells us how to find out the general solution of the linear partial differential equation of 1. Then its solution is given by equation number 2. Capital F is some function of u and v. This is f of uv equal to 0, where this f is an arbitrary function, u is a function of xyz, and v is also some function of xyz. Equation number 2 can be written as f of uv equal to 0, or we can write u as a function of v or v as a function of u. In all these three forms, we have one arbitrary function. Now, how to find out, or what are these u and v functions? Here this u equal to constant and v equal to constant, they form a solution of the equations given by 3. 3 we call as auxiliary equations corresponding to the partial differential equation 1. We have equation number 3 as dx upon capital P equal to dy upon capital Q. This is equal to dz upon capital R. Here the auxiliary equation 3, which is dx upon P equal to dy upon Q equal to dz upon R. So I can rewrite this in form something like a equal to b equal to c. So these are actually two equations. We can say a equal to b or a equal to c. In that case, b equal to c is automatically satisfied. So this equation number 3 represents two equations, and using these two equations, we find out two functions, that is u as a function of xyz and v as a function of xyz. Now consider the general case when z is function of n variables x1, x2 and xn, then the Lagrange partial differential equation is given by 4, where we have n functions p1, p2, pn, all capital Pi's, and derivative of z with respect to x1, with respect to x2 and with respect to xn. And on right hand side I have r as a function of x1, x2, xn and z. Then the general solution of partial differential equation 4 is given by capital F, which is function of u1, u2, un equal to 0. That is equation number 5. Capital F is an arbitrary function, and this u1, u2, un, they are functions of xi's and z and form a solution of the equations given by 6. That is dx1 upon p1 and then dxn upon pn. This is equal to dz upon r. There are n independent variables, so we are finding n functions. In the previous part, we were having 2 independent variables, so we find 2 functions. One is u and second one is v. Here I am mentioning a very simple result, that if we have 2 ratios a by b and c by d, if they are equal, then we can multiply these ratios by same number, like alpha over a, this is equal to alpha over b. This is equal to beta over c divided by beta over d. And alpha and beta, they are real numbers, non-zero I am taking. This one is called componendo and dividendo rule. So if 2 ratios are equivalent, then you can add them numerator wise and denominator wise. You can subtract them, or you can multiply them by some numbers, same number in numerator and denominator. Similarly, second ratio you can multiply by some different number, say beta, and again you can add them. The ratio is always going to be same. We will use this while solving this auxiliary equation for the partial differential equation to find out the general solution. So just take simple example here. Suppose we have dx upon x square. This is equal to dy upon y square. This is equal to third ratio dz upon x plus y into z. Then we can multiply the first ratio, that is dx terms, by y numerator as well as denominator, and we get the fourth term here. I have marked by arrow that multiply the first ratio by y numerator and denominator. Similarly, we can multiply the second ratio with dy by x, and we have the last term x dy divided by x into y square. Right? Now we will use the above result, that if 2 ratios are equal, we can add them numerator wise, we can subtract. Now we can add last 2 fractions, ratios, and we get y dx plus x dy divided by xy into x plus y. In the last one we have, and I can compare with the third ratio, that is dz upon x plus y into z. So we will do something like this while finding the general solution of partial differential equation. Consider example number 1. We have to find the general solution of a partial differential equation given by 1. Here capital P is x square, capital Q is y square, and capital R is right hand side of equation number 1, that is x plus y into z. The general solution is, sometimes we say integral surface also. So the integral surfaces of equation number 1, they are generated by the integral curves of the equations, auxiliary equation dx upon p, this is equal to dy upon q equal to dz upon r. Now in this auxiliary equation, put the value of capital P, Q, and R. Now we have equation number 2. Now we have to solve these two equations given by equation number 2. Most of the time, one combination is easy. Second one can be calculated by little bit of calculations or arrangements, right? So here I have taken first two terms marked as star. We have x and y, and we have just dx and dy, two variables only. So it is going to be something similar to the ordinary differential equations. First order ordinary differential equation, you can solve this by any of the techniques. So if I just consider first two terms given by a star, we have dx upon x square, this is equal to dy upon y square. I can easily integrate this one, and I have minus 1 upon x plus 1 upon y equal to c1 dash, or you can simply say 1 by x minus 1 by y, this is equal to c1. So we have first integral curve, that is u of x y z equal to 1 by x minus 1 by y. Now we have to find the second curve. Till now we have just used first two terms of the auxiliary equation. We have not used third combination, that is with dz. So to find out the next one, we have to make sure that we are using third term, that is dz upon x plus y into z. If you see third ratio in the auxiliary equation, with dz we have z in the denominator and we have x plus y also. We can't integrate it because with the dz we just want terms of z only, right? So to simplify this, we can use componendo and dividendo or any sort of combination with the three terms given in the equation number 2. So now what I am doing, take the first two terms and find out the difference of these two. So dx minus dy divided by, I am subtracting the denominator also. So in denominator we have x square minus y square, and I can compare with this the third term, that is dz upon x plus y into z. Now in the first ratio, I can simplify the denominator. We have x square minus y square. I can rewrite this one as x minus y into x plus y. Now in this dz and dx minus dy terms, see the denominator part, x plus y is appearing in both the terms. So we can cancel x plus y from both sides, and finally we have dx minus dy divided by x minus y, this is equal to dz upon z. Now this form is integrable. We can integrate both sides. We get ln x minus y, this is equal to ln z plus ln c2. Further we can simplify this. So we have v as a function of x, y, z, and this is given by x minus y over z, this is equal to c2. So the general solution of this partial differential equation is given by capital F, an arbitrary function. Then I am writing u 1 upon x minus 1 upon y, comma v, that is x minus y divided by z equal to 0. We can rewrite this general solution in two other forms, u equal to some arbitrary function of v, or v as some arbitrary function of u. So out of these three solutions given by capital F, capital F1 and capital F2, all are same. Now as we discussed earlier that we have to solve the auxiliary equations, you can use any combination. So one student can go for one particular combination, other student can try some other combination. So you can have different solutions. So I'm discussing one more solution here. Consider the first two terms with dx and dy. Multiply dx by y and dy terms with x and add them. We will get the first ratio. y dx plus x dy divided by xy is common, and then we have bracket x plus y. Now I can compare this combination with dz term, and now x plus y in the denominator is same, so we can cancel out, and finally I can write down the denominator with dy and dx as differential of xy divided by xy. This is equal to dz upon z. Now this is in integrable form. Now we can integrate this. We get ln xy minus ln z equal to ln c3, and finally we have xy over z. This is equal to c3. Now we have three functions now here: 1 upon xy minus 1 upon y, x minus y divided by z, and third one is xy over z. Now out of these three functions you can use any of the functions, the value is always going to be same. This third function is as such looking something new, but actually it is not new function. This function xy over z, it can be obtained by some sort of combination with earlier two functions, that is u and v. I will discuss this in numerical problems also. Here we can divide v by u, the function v which we have calculated using the auxiliary equation. So if you divide v by u function, you can get the third combination xy over z equal to c3. Consider example number 2. Here I am taking u as a function of three independent variables x, y and z, and it satisfies the partial differential equation given by 1. We have three derivatives here: partial derivative of u with respect to x, with respect to y, with respect to z. Here right hand side is 0. As there are three independent variables, so we will find out three integral curves from the auxiliary equations, right? Here we have to show that u contains x, y and z only in the combinations x plus y plus z and x square plus y square plus z square. Now to solve this one, we write down the auxiliary equations given by 2 dx upon y minus z, dy upon z minus x, dz upon x minus y. This is equal to du equal to 0. So as I told you, these are three equations. So we solve them and we find out three curves. First one is the last one, du divided by 0. So here I can say that du equal to 0. Only then it is going to make sense, right? So du equal to 0. So this implies that u equal to some constant. We have first integral curve. Now we have to use the remaining terms. See, the first three terms I have marked as star 1, star 2 and star 3. If you add all these three terms, then the denominator will be 0. So we have the next combination. So dx plus dy plus dz divided by, add all the terms, denominator is 0. This is possible only if dx plus dy plus dz equal to 0. You can integrate this expression, and finally we have x plus y plus z equal to c2. That is the second integral curve. Now we have to find one more. Before starting that, if you see the auxiliary equation number 2 on the previous slide, the first three terms, we have the denominator part x minus y, y minus z and z minus x. So they are symmetrical. So if you have some symmetry in the expressions, you always try few combinations. If you are not able to find directly, dx plus dy plus dz. Second combination is x dx plus y dy plus z dz. So here I am trying that second part, that x dx plus y dy plus z dz. then the denominator will be like this, and denominator is 0. Denominator is 0, then numerator should be 0. Otherwise we will get something like infinity, which is not possible. So finally we have this second last expression, x dx plus y dy plus z dz equal to 0. Now we can integrate this. We have finally equation number 5, x square plus y square plus z square equal to c3. So now we have 3 integral surfaces, and now we can write down the general solution of the partial differential equation. So the general solution of the differential equation 1 is given by capital F, any arbitrary function, with 3 arguments u, comma x plus y plus z plus x square plus y square plus z square. Or you can write in other form u as some arbitrary function of x plus y plus z and x square plus y square plus z square. Consider example number 3. We have to find out the general integral of the linear partial differential equation given by 1. Here capital P, Q and capital R we can read from equation number 1, and the auxiliary equations are given by 2. Dx upon zx, this is equal to dy upon minus yz equal to dz upon y square minus x square. Most of the time we look for a combination where we have to deal with 2 variables, because it is easy to simplify that part. If it is not available, then we have to look for the combinations. So if you see the first 2 terms here, I have marked as 1, 2 and 3. So 1 and 2, we have dx and dy, but in denominator z is common, so we can cancel out z. So the first combination is dx upon zx equal to dy upon minus yz. Cancel z on both sides. Simplify this. We have dx upon x plus dy upon y equal to 0. Now we can easily integrate this one, and finally we have xy equal to c1, which is the first integral curve for the partial differential equation. Now we have to use third term of the auxiliary equation also. In this we have dz divided by y square minus x square. So in this case we have to simplify this so that we can integrate dz expression, and for that we need terms of z. So we can use first 2 terms here, add first 2 ratios. From the auxiliary equation we get dx plus dy, and the denominator will be z times x minus y. Now I can compare this ratio dx plus dy with dz. Factorize the denominator of dz. We have x plus y into x minus y with minus sign. Now if we see these 2 expressions, I have marked with arrow, we can cancel x minus y on both sides. And finally we have dx upon x divided by z. This is equal to minus dz upon x plus y. Now we can cross multiply these expressions, and finally we have x plus y into differential of x plus y plus z times dz equal to 0. Now it is in integrable form. And finally we have equation number 4. Hence the general solution of partial differential equation 1 is given by capital F as a function of xy, comma x plus y whole square plus z square equal to 0. Here I am discussing one more combination. While finding the second combination on the previous slide, we took the sum of first and second ratio. Now we can take the difference also, dx minus dy, and again compare this with dz. If we simplify these terms, see the first equation here, I have marked, you can cancel x plus y now. And finally we have terms like dx minus dy divided by z. This is equal to minus dz upon x minus y. Cross multiply these two expressions and now we can integrate them, and we have equation number 6 as x minus y whole square plus z square equal to c3. Now out of these three integral curves, you can pick any of the two integral curves and you can write down the general solution of the partial differential equation. In this example, we have calculated three integral curves given by equation number 3, equation number 4 and equation number 6. Here we observe one thing, that equation number 6, it can be easily obtained by equation number 3 and 4. Let's see. From equation number 4, we have x plus y whole square plus z square equal to c2. Now x plus y whole square can be rewritten as x minus y whole square plus 4 times xy plus z square equal to c2. Right? Second equation on this slide. Now I am using equation number 3 because our integral surface are such that here x plus y is equal to c1. That is equation number 3. So here we can substitute here 4xy, we can put xy equal to c1. Now we can combine these two constant terms, c2 minus 4c1, and this is some new arbitrary constant, c3 star. Now see the expression on the left hand side. It is x minus y square plus z square equal to c3 star, and this is exactly the same form as equation number 6. So we can have different forms, but overall structure of these equations or integral curves will be this, that we can find out one expression from the other. These integral surfaces are the surfaces or the curves which are satisfied by the general solution or the solution of the partial differential equation. Consider the partial differential equation given by equation 1 with capital P, Q and R. We can write down the auxiliary equation dx upon y square, this is equal to dy upon minus xy, this is equal to dz upon x into z minus 2y. I am writing these expressions as 1, 2 and 3 so that we can refer these expressions while doing the calculation. So see the first two terms here, dx and dy. We just have two variables x and y, and denominator also we have just x and y. So we just pick the first combination as first two ratios, compare them. Y is common in the denominator, we can cancel out. Now cross multiply, we get x dx plus y dy equal to 0. We can easily integrate this and we have the first integral curve x square plus y square equal to c1. Till now we have not used third ratio, that is dz upon x into z minus 2y. So to find out the second integral surface or curve, we will use this ratio with the dz term, and along with this we can use any combination of first and the second or just one of the ratios. So I am using second and third ratios, dy upon minus xy, this is equal to dz upon x into z minus 2y. Cancel x from this one, cross multiply. Now this is first order ordinary differential equation. You can solve it by any of the techniques, starting from the exactness, variable separable if it is feasible here, or regrouping, Leibniz linear differential equation, any of the forms. Here I am using regrouping technique. So I can rewrite this one after cross multiplication, z dy plus y dz minus 2y dy. The first two terms I can combine and rewrite as differential of yz, and second term can be written as differential of y square. Now we can easily integrate, and finally this is yz minus y square equal to c2, that is equation number 4. This is the second integral curve. So the general solution of the partial differential equation is capital F as function of x square plus y square, comma yz minus y square, given by equation number 5. Consider example number 5 now. Partial differential equation 1. We can write down the auxiliary equation for this one, that is equation number 2. dx upon y plus zx, this is equal to dy upon minus of x plus yz equal to dz upon x square minus y square. So in equation number 2, I am writing them as 1, 2 and 3. Now we have to look for the combination. First we try to look for a combination where we have just two variables. But in this expression all the variables x, y, z are mixed, so we have to look for some calculation. So we'll try to see with the dz, we have denominator as x square minus y square. Now see the first two terms, dx and dy. In the denominator we have, with dx we have zx, and with dy we have yz. So if somehow we can make some combination so that we can cancel out z. So what I am doing, multiply the dx ratio with y, and with dy I multiply by x, so that we have xyz in dx term, and in dy ratio we have again xyz but with negative sign, and finally we can eliminate z. So what is the first combination here? Multiply first ratio by y, second ratio by x, and add them. Whatever we get, we equate that with the third ratio. So finally we have y dx plus x dy, and in the denominator we have y square minus x square, and this xyz term will cancel out. Now compare this with dz term, right? So finally we have these two ratios. In the denominator x square minus y square is same, so we can cancel out, and finally we can integrate it, and it is now differential of x over y, x into y, plus differential of z equal to 0. Integrate this, we have finally integral curve xy plus z equal to c1, given by equation number 3. Now for the second combination. As such, there is no hard and fast rule or any specific technique for finding these one. You have to scan carefully what are the terms in numerator and denominator, how can we use these one, and with practice you will learn these techniques. So let's try the next combination. Add first and the second term in auxiliary equation 2. We get dx plus dy over denominator will be y plus zx minus x minus yz. So see the next expression here. I can take y minus x common. So finally dx plus dy, and the denominator will be y minus x and 1 minus z. Now I can combine this with dz term. And dz denominator we can write down as minus sign y minus x and y plus x. Now in these two ratios y minus x is same, we can cancel out. Now cross multiply the terms. After cross multiplication we can easily integrate these expressions, and finally we have equation number 4 as the second integral curve. So the general solution is given by f function of xy plus z comma x plus y whole square minus z square plus 2z equal to 0. Here I am discussing one more possible combination. We can take the difference of first expression and second expression, that is ratios in the auxiliary equation, and then we can compare that with the third ratio dz. So if we subtract dx and dy terms, we get dx minus dy over x plus y into 1 plus z. This is equal to dz upon x square minus y square. Now x plus y will be cancelled out, and finally we have dx minus dy divided by 1 plus z. This is equal to dz upon x minus y. Now cross multiply this, integrate it. We have the third combination given by equation number 6. So you can use this combination or the previous one also. Consider the partial differential equation given by 1. We can write down the auxiliary equations here. See the equation number 2, dx upon x into z minus 2y square. This is equal to dy divided by y into z minus y square minus 2x cube. This is equal to dz divided by z into z minus y square minus 2x cube. I am denoting these three ratios as 1, 2 and 3. I have marked these numbers by red color. Now we have to look for the combinations now. See the second and the third ratio. If we see the denominator part, z minus y square minus 2x square, we have same expression. So we can cancel this one, and now we have just two variables y and z. So compare second and the third ratio. In the denominator, cancel the common term, and we have dy upon y. This is equal to dz upon z. And finally, we can integrate this, and we have the first integral curve z equal to c1 times y given by equation number 3. In this numerical problem, second combination is little tricky. So later on I will discuss the technique that if you are not able to find out second combination or second integral curve, then how to simplify the problem. Now I am rewriting auxiliary equation here. We have already used second and third ratio. So we have to use first ratio while finding the second integral curve. Now for this one, see the first ratio. With dx we have x in denominator and x is multiplied with z minus 2y square. So if with dx somehow we can cancel this z minus 2y square, then we can simplify this further. So for this one we will use second and third ratio. In second and third ratio, y and z part, the remaining expression is same. So we take dz minus 2y dy, so that in denominator we take the expression z minus y square minus 2x cube common, and the remaining part will be z minus 2y square, and it is same as the expression in the denominator. In the first ratio I have marked it by red star. So the combination is third ratio minus 2y times second one, so that is dz minus 2y dy, and the denominator part will be z minus 2y square, z minus y square minus 2x cube. Now we compare this first ratio and the fourth ratio. Now in this one, this part z minus 2y square is common and it is cancelled out. So we have equation number 4 now. I am rewriting equation number 4 here. After cancelling z minus 2y square, we have equation number 5. Now say this equation number 5 carefully. Ratio number 5th and 6th I have marked. In the 5th ratio, if we take the differential of the denominator, it will be dx, and it is same as the numerator of this ratio, so we can easily integrate it. But if we see the right hand side, that is ratio number 6, take the differential of the denominator, it will be dz minus 2y dy. These two terms we already have in the numerator part in equation number 5 on right hand side, but this x cube we don't have. So if somehow we can accommodate or we can simplify this x cube part, we can look for some solution, right? So what is the differential of x cube? It is 3x square dx. Now luckily on the left hand side, that is the 5th ratio, we have just terms of x. So what we are doing, multiply 5th ratio by 3x square and see what we have. I have written the combination 6th ratio plus 3x square into 5th ratio. Keep the 5th ratio on the left hand side as it is, dx upon x. This is equal to 6th ratio, and just in this I am adding 3x square into 5th one. So on the right hand side I have dz minus 2y dy plus 3x square dx. And see the denominator part here, it will be z minus y square plus 3x cube minus 2x cube. Simplify this denominator. Now we have equation number 6, and on the right hand side denominator is z minus y square plus x cube, and now we can easily integrate this one. Finally, equation number 6, we integrate both sides, and finally we have the solution z minus y square plus x cube divided by x equal to c2 star, equation number 7, and the general solution is given at the end. In this previous example, the second combination was quite tricky, and it's not always easy to guess this combination. So if we are not able to find second combination and we already have one integral curve, then this integral curve or surface can be used to find the second integral surface. So we have two surfaces actually, u function of xyz equal to constant c1 and v as function of xyz equal to c2. Now this integral surface u equal to c1 and v equal to c2, it means that the solution of the partial differential equation is such that the points xyz lying on the surface, that is the general solution, they satisfy these equations. So given one function u xyz equal to c1, we can use this and we can find out z in terms of x, y and c1, and we can use this in the auxiliary equation. So what exactly we are doing here? We already have one integral curve u as a function of xyz and constant c1. So we can use this relation. Whatever will be the general solution of the partial differential equation, those variables x, y, z, they are going to satisfy this equation u equal to c1. So we use this surface u xyz equal to c1. We find out one of the variables. Say I am finding suppose z in terms of x, y and c1. I can substitute this value of z in the auxiliary equation, and I can just work with two variables x and y, and we find out the solution of that. Once we have the solution, we will have c1 in that part. So we again substitute the value of arbitrary constant c1, and finally we have some solution in terms of x, y, z and second arbitrary constant c2. I'm discussing the same numerical problem with this technique if we are not able to find out the second combination for the integral curves. I'm considering the previous numerical problem. The auxiliary equation is given by the first relation here. The first solution is quite easy. We just use the last two ratios with the dy and dz, and here we have z as given by star, z equal to c1y. Now we have not used the first ratio here with the dx. So now we will work with dx. Second one you can choose, you can pick dy, you can pick variable z also. So here I am substituting z as c1y, and I will convert everything in terms of only x and y, and we eliminate z from the auxiliary equation to find out the second integral surface. And we will see at the end that we are getting the same combination as we got in the previous example, right? Now substitute the value of z in the first two ratios with dx and dy. So z is c1y. I have marked the position of z with red. Now if you see the first ratio with dx, we can take a y common from the denominator and cancel out. After cancelling y, we get dx upon x times c1 minus 2y. This is equal to dy divided by c1y minus y square minus 2x cube. Now this is first order ordinary differential equation. You can again apply any technique to solve this equation, starting from regrouping, exactness, Leibniz linear differential equation, or any other form. Here I am solving this using the exactness. I will check whether equation is exact. If it is exact, we can find out the solution. If it is not exact, then we can make this equation exact by multiplying with suitable integrating factor. So now in this ratio, dx upon and dy upon cross multiply and write down your equation in the form m dx plus n times dy equal to 0. Now we check the exactness. Derivative of m with respect to y, it is c1 minus 2y, and derivative of n with respect to x is minus of c1 minus 2y. Clearly it is not exact. Now we look for some suitable integrating factor for this one. Now to find out the integrating factor, take the ratio derivative of m with respect to y minus derivative of n with respect to x divided by n. And if we simplify this ratio, we are getting minus 2 upon x. This is function of only x. So yes, the integrating factor is e raised to power minus 2 upon x dx, and on simplification it is 1 upon x square. So now we multiply the equation on the previous slide, that is double star I have marked. Multiply that equation by 1 upon x square. We get the next equation. If you want, you can check the exactness of this equation, and clearly it is exact now. Now once it is exact, we can find out its general solution. The general solution of an exact differential equation is given by integration of m, capital M, with respect to x, treating y as constant, plus terms of n independent of x. We integrate those terms with respect to y. This is equal to some constant c. Put all the values. There is no term of n independent of x, so the second part will be 0. Now we can integrate the expression of m with respect to x, treating y as constant. So finally we have this solution minus 1 upon x into c1y minus y square minus x square equal to c. Now we can multiply by minus x on both sides. Do that thing. And now put the value of c1 here. c1 is z over y. And when we put the value of c1, we get this expression in the box. z minus y square plus x cube upon x equal to c star, and this is exactly the same solution which we got from the combination. Try these numerical problems and find out the general solution. I have written answers for all these problems, so you can have little bit of idea about the combination, but try to solve them independently. If you have any problem, then you can see the solution and look for the combination also.